All right, so example one. Find the critical points of this function and identify the open intervals in which it is increasing and which it's decreasing. And I gave you a little box down here for it. So what do we have to do first? To find the critical points are where the first derivative is equal to 0. So we got to find the first derivative of our function. 3x squared minus 12. Then set that equal to 0. Move the 12 over. Divide by 3. So x squared equals 4. Square root it, so x equals plus or minus 2. That's the easy part. Now we got to find the intervals for where it's increasing, decreasing.
Okay.
So the intervals are going to be from, because our -2 and 2 are our critical points.
Right.
So everything on this side, everything between here and everything here are our intervals. -infinity to -2. -2 to 2. And 2 to positive infinity. So, because what happens at -2 and 2? Why are those called critical values?
Because that's when the slope is 0.
That's exactly. Those are the vertices. So what we have to do is pick a value that's not on this domain. I mean, it's not that a critical point. So let's pick -3. If we can, in the middle one, we'll use 0, and the other one we'll use 3. So what we do here is we plug in these values into our first derivative. And all we really care about is the sign. And our first derivative is 3x squared minus 12. So we put -3 in there. -3 squared is 9 times 3 is 27. 27 minus 12 is 15. It's positive. Since it's positive, it's increasing.
Okay.
And at 0, 3 times 0 is, so it's -12. So the sign is negative, which means it's decreasing at that side. So what do we know about -2? Since it's increasing there and it's decreasing there, -2 then is a maximum.
Okay. Yep. That makes sense.
And on this side, it's so at +3, it's going to be the same as -3. So it's going to be positive 15. So it's increasing. So at +2, we have a minimum. So that's what it's telling us.
At +2.
At +2, yeah, because to the left of it, it's going down. To the right of it, it's going up.
Right.
Okay, once we find the critical values, we take a point on both sides. I picked -3 and I picked 0. The intervals? Well, since this is our first interval. It starts at -infinity and goes all the way to here. Then it goes within these two. And then it goes here. So we're going to go through all the intervals that include -2 and 2 as endpoints. So notice that's -2 there, -2, +2, +2. So that's how we determine increasing, decreasing of maximum minima. And here's another example. So at the endpoints, remember, we can use the endpoints. Since at A, it's the lowest of the entire picture, it's the absolute minimum. And the highest point is at that point. So that's the absolute maximum. But since it's a point, remember, you cannot have first derivatives at points or edges or corners. So that's why the first derivative is undefined there. But it is the absolute maximum because the F point is there. What actually, with what we talked about yesterday, what do we have at this point here?
Valley.
Yes, but remember in section 4 we talked about concavity. So what happens at that point?
Okay.
Because you notice this side it's concave down, this side is concave up.
Oh, that's
Point of inflection. Yes, very good, very good. That's the point of inflection. Because it stops going down, starts going up, and this is continual down. Same thing here. At this point here, approximately, it stops being concave down and begins to be up. So we have to look at all these things, and these are all local maximum minimas. Let's look at example 2. Now with this one, it says identify the open intervals in which f of x is increasing, decreasing, then find the function's local and absolute extreme values. Oh, I forgot to put a box there. Oh well. So what do we do first?
We have to find the first derivative.
Find the first derivative, right? So we could do it. We could either do it by a product, or we could distribute that and just do it in pieces like that. I think it's easier doing this way. So it's 4/3 x 1/3 minus 4/3 x to the power what? -2/3. Very good. Because we subtracted by 1, which is 3/3. So what do we do next? We have those. Let's see what they look like actually. We have 4/4 cube root of x over 3 minus 4/3 cube root of x squared. So what do we have to do next? We have to simplify that equation, but how?
You have to get common denominators.
Okay, we could do that. So if we do that, they both have a 3. This one has a cube root of x squared. So we have to multiply the first one by the cube root of x squared, top and bottom. So now what happens on top is we have cube root of x squared times cube root of x. Since they're both cube root, we can multiply inside there. X squared times x is x cubed, which just gives us x. So we have an asymptote at 0. We can't have a 0 in our solution. So what's our 0 points? If we set this equal to 0, what do we get? The only way a fraction can equal 0 is if what? Can the bottom ever be 0?
The numerator is 0.
Only the numerator, yeah. So the only way this could be 0, so we set that equal to 0,
It's
4x minus 4, so x is 1. That's our 0, that's our critical value. And we also have another one, is x cannot equal 0. So what is our intervals? If we look at the number line, we have 0, we have 1. Well, we can't use that one. So our intervals are here, here, and here. So it's negative infinity to 0, 0 to 1, and 1 to infinity. So now we got to figure out whether it's increasing or decreasing. Okay, those are the open intervals, increasing. Now we got to figure out whether increasing, decreasing. How do we do that? Pick a value in this domain.
So we'll do -1, plug it into 4x
Right.
minus 4.
Yes. So this is what we put in the first derivative. And the second one, between 0 and 1, let's use 1/2. And between 0 and infinity, let's use 2.
Okay. So 4 times -1 minus 4 equals -8. Or yeah,
Negative over.
over
over.
3 cube
Over.
cube root of x squared.
Yeah, so basically the bottom can never be negative.
Right. So
So
that would
because it's squared. So only thing we look at is the top. If the top is negative, the whole thing's negative. So
Right.
this one's negative, so it's decreasing. It's going down. At 1/2, we put 1/2 inside there. We have 4 times 1/2. 4 divided by 2 is 2, minus 4 is -2. Also negative, also decreasing. And then at 2, 4 times 2 is 8. 8 minus 4 is 4. It's positive, so it's increasing. Basically, what we're looking at is, since we know our points of interest are at 0 and 1, the function's decreasing, it's decreasing more, and then it's increasing at 1. So it looks something like this.
because it has a greater slope over the other interval. Over over -infinity to 0.
Well, yeah, because negative infinity 0 has a negative slope, so it's decreasing.
Right. Okay, so but I was just so it's just more steep, right?
Well, the steepness we can't tell yet,
Okay. Okay.
but well, we could assume it because the coefficient of the numerator is 4, so it'll be pretty steep.
Okay.
And somewhere between 0 and 1, we'll have a vertex. Well, at 1, what happens at 1 then? Let's see what happens at 1. 4 minus 4 is 0. So it's 0. So it's 0 there, yeah. So that's our function there. So the hardest part is if you have radicals or trigonometric functions, then it becomes more of a pain. All right, find the critical points, identify the open interval, and tell me whether it's local. Oh, we haven't done the extrema. At this point, we have a absolute minimum,
Okay.
and we have no absolute maximum because it goes on to infinity both ways. It's absolute and it's also local. Let's look at number 3. Either way, we're going to have to do a product rule. Or is there another way we could do it? Not really.
Not that would be easier anyway.
Right. So this is our F and this is our G. F, G, F prime, G prime. X squared minus 3. So this one's 2x. This one's EX and this is EX. So F prime is 2x EX plus x squared minus 3 e to the power x.
Then we set that to 0.
Well, we have a common factor here. So we have 2x plus x squared minus 3, which makes it a quadratic equation. Ex x squared plus 2x minus 3. Because if we couldn't set it to equal 0 because we have two separate functions, now we just have a product. This one can never be 0. So the only one that can be 0 is that one. So we set x squared plus 2x minus 3 equal to 0. And we can factor this one. Yeah, so it's x plus 3, x minus 1. So the zeros are at -3 and +1.
Wait, why do we put the e to the x on the right side of the equation?
Oh, you can put it anywhere you want to. You can put it in the back of it if you want to. It's commutative.
Oh, okay, I see.
I just factored it out first, and then whatever's left, I put in parentheses behind it.
Oh, okay. I thought you were saying that e to the x of, or yeah, e to the power of x times 2x plus x squared minus 3 was equal to e to the x. Okay, I see now.
No,
Okay.
oh no, there's an equal sign right there.
Okay.
Yes, so since they both have e to the x's, so we just look at the coefficients and put them together, which makes it a quadratic equation. So
Okay.
our critical points are at -3 and 1, which these are our intervals. To 1 and 1 to positive infinity. Let's pick a number here. Let's pick -4, 0, and 2. Again, all we need to know are the signs. Is it increasing or decreasing? The E of X can never be negative, so we don't have to worry about that. So we just worry about this, these are here. So -4 + 3 is -1. -4 - 1 is -5. That makes it a positive. So it's increasing. At 0, we have 3, -1, which makes it a -3, which makes it decreasing. And at 2, we have 2 + 3, 2 - 1. They're both positive. So on this side is increasing. So this side is decreasing, this side is increasing. So we have a minimum here. We have a maximum here. And we can't check the endpoints, but what do we know about this function? What's the graph going to look like?
Well, it's gonna have both ends going up.
Both ends going up. Yeah, that's for this part here, right? Because it's a quadratic equation. But because of the E of X, remember, how does the E of X look? It's an increasing function. So the quadratic equation looks like this. So we know that the right-hand side will keep on going up forever. Now the left-hand side will even out so that it'll give us an asymptote of some sort. It's going to damper out. Either going to go up or down. We have to look at calculations for those.
Okay. Depending on
But either way, it's never going to cross the x-axis.
right.
Which means if it goes down, then at -3, we have a relative maximum. So it has to start going down. Because remember, at -3, on the left-hand side, it goes down. So this is what the graph's going to look like. It goes down here, it goes down there, and it goes up here. That's what the graph tells us.
So
Now-
we have two graphs essentially. What
Well, we have to take them both. We have the E to the X and we have the quadratic equation.
right.
Yep. And whatever is the more powerful one will dictate that. Well, in other words, look at this one. Since we know that negative at 3, -3 and +1, and both, if it is just the quadratic equation, we know it looks like this, right?
Mhm.
Both ends go up, which means between here we have negative numbers. So between -3 and 1, the quadratic equation is negative. So that means these values here, we have to have, if that's 1, we'll have to have negative values between there. So in other words, the graph has to be below here in this interval.
Mhm. Over -3 to 1,
Right.
and that's going to be the quadratic equation,
Because of the quadratic equation is negative between those two.
and the exponential is always positive. Okay, I see.
So that's why we have to look at both of them. I mean, this is without using a calculator or graphing. This is, you have to look at the equations, what you have. This one's never negative. This was only negative between here. So we know between somewhere here that the graph has to be negative. So we'll have to have an x-intercept. Well, we know where the x-intercepts are. If we set that equation equals 0, so we have x squared minus 3 equals 0, x squared equals 3. So x equals plus or minus radical 3. Those are your x-intercepts,
Right.
which is approximately, it's less than 4. The square root of 4 is 2, so it's between the 1s and the 2s. So let's say there and there are our intercepts. And we can figure out at 1 is -2. So yeah, our graph is going to look something like this.
So with the derivative, we're getting an image of what the graph is going to look like before plotting points,
Right.
basically.
Because it tells us where our vertices are.
Right.
We look at the vertices are going to be at -3 and 1. Somewhere along those lines will be a minimum. So we compare that with the original function and see what happens to all these terms.
So we can find exactly what the minimum and maximum are.
Yes, and the intercepts. Take the original equation, find the intercepts, so we know it crosses there and there, or there and there, it crosses. And we have to have a minimum at 1 and a maximum at -3.
Mm-hmm.
So we know that this has to occur. And then from 1, it has to go back up. And then back down. So that's what it's telling us.
Okay. Okay.
First derivative only tells us where the maximum minimum are. The regular function tells us where the intercepts are, and then we have to connect the dots.
Okay. And so I mean, if you were to use like a computer algebra system, because I know in the textbook there's a few exercises that require you to use a computer algebra system, and I've never used one before.
Yeah,
Can-
me neither.
Can you? I mean, like it looks kind of difficult, but I'm gonna start trying to do it.
Actually, you don't need to. All you have to do for these, did you ever use Desmos?
No, I've never used it.
Oh, let me introduce you guys to Desmos.
Oh,
Yeah, Desmos is just that. It's a. Oop, let me move this out. Let me show you what this is. Go to desmos.com. Let me move my thing back up. Desmos is just it's a graphing calculator.
Oh, but it does 3D graphing?
It does now. It's in beta, but it originally just gives you, wow, it doesn't, now it is going to give you 3D. Wow. Okay. So all you do go over here is just type in your function. E to the power, arrow up. So that's changed. I gotta figure out where all their, because they used, there it is.
Oh, you were trying to do the arrow like the programming language way.
Yeah. So that's S to the power X. Oop. I don't want that one. Open parenthesis, it was X squared. No. What was it? It was X squared plus 2X minus 3. Oh, since it's 3-dimensional, I think we're going to need a Y equals. So there it is in 2 dimensions. This is the X-axis, that's the Y-axis. So that's our intercept here, and that's our second intercept. It's at negative radical 3, positive radical 3. And it keeps on going, but then it tapers down next to the X-axis. So that's pretty much what we had.
Yeah, I mean, so we can get really a pretty close idea of it without even plotting any points.
Yeah, that's why I love playing with 3D graphs.
Yeah, look at that. That's cool.
Lewisham? Yeah, exactly. We could just. I don't
This
know.
is like a great way to get a good visual image of it, especially with the 3D.
Yes, I'm trying to see where we can get it to be just a regular 2D.
Oh, add Z maybe to it.
This it already has a Z. So I mean we could put a Z in the function.
Well, if you Z equals, is that what the thing says?
Well, yeah, it's gonna be Z equals automatically because if I don't have to put it's implied that it's Z equals.
Oh, I
And
see.
I put a Y value in there, 2Y minus all those values of X. Let's make it. It's so cool how, I mean, when this thing just changes.
Oh, you have to insert those Y's into the
Right, you have to put them in there. And then you could rotate it.
wow.
Oh, there's your traditional one. If you look down the Z axis.
Mm-hmm.
So if we look down the in the regulars. Let me get rid of these Y values now. So I have Y equals. There. But yeah, this is Desmos. It's pretty cool because what I show my algebra students when we talk about quadratic equations, you have ax squared plus bx plus c. And I ask them, what does this do? What does this do? I'll show you. So I have y equals ax squared. Nope. Plus bx plus c. And now I come over here and now I can have, let's say I want everything to be at, if a is 0, it's a linear equation. It's bx plus c. If a is 1, and we don't have a c or a b,
And you're just okay, so you're just showing them transformations.
right? And that's what happens now when we have a c. When c gets positive, what happens to the graph? It goes up. It's a horizontal shift because it's the c is away from the x's. And if it's negative, it goes down. So that's what the c value does. And what does b do? B is in essence, it rotates about the
Origin, yeah.
origin.
That's cool. That's a really good like learning aid or visual aid.
Yeah, and if A is between 0 and 1, it gets wider. If it's greater than 1, it's right. Yeah, it's horizontal. But if A is negative, it goes down. So that's the leading term test. But yeah, this is what, if you ever just want to see what a function does in the homework assignments, plug it in Desmos and see what happens.
Yeah, I'm going to start doing that more often now.
Yeah, because it's a very, very, very interesting and a very, very good program for it. Okay, now I have section 4 homework. And section 4 is when we dealt with concavity. Holy smokes, he's printed out crooked. So back to our class. Look at this, how it printed out. So concavity up is if the second derivative, concave up, on one side it's increasing, the other side is decreasing. So if its second derivative is positive, then it's concave up. If the second derivative is negative, it's concave down. So let's look at example 1. Find the intervals where the following function have concavity. Okay, I'm sorry, let me put that up there. So you write it down. Write down the first 2 examples, then we'll do those. All right, so example 1. This is Math 2413, day 20, the end of the 10th week, chapter 4, section 4, examples. So example 1, we have y equals x cubed and y equals x squared. Find the intervals where the function have concavity. To find the concavity, we have to find the second derivative. And
So they're both concave up.
well, how do we know they're concave up?
They both have leading coefficients that are positive.
Well, we have to first set them up to be 0. And let's just do this one first. So when x is 0, so what happens there? What happens when x is 0?
It equals 0. The equation equals 0.
Well, the second derivative equals 0.
Right.
Well, and so in other words, we know that this function is a cubic function. It goes through the origin. So this one tells us that increasing. So let's look at, since that's our important point, this is actually our point of inflection. I'm gonna call it the POI from now on. When we said the second derivative equals 0, that's where it changes. On this side, it's gonna be concave down. This side's concave up.
So we
Well,
have,
how do we know? Only thing we know that because if we have a point of inflection, that means we have to have 2 concavities. So how do we check the left side? Well, since the point of inflection is at 0, let me try -1. If I put -1 in there, I get -6. Since the second derivative is less than 0, it's concave down. And likewise, on the other side, at 1, if the second derivative is +6, it's greater than 0, so it's concave up. So the intervals tell us what? From -infinity to 0, we have concave down. Then from 0 to +infinity, we have concave up. And that's what intervals where it's concavity. Yeah. So there's the concavity for that one. How about this one?
so that one doesn't have a point, or well,
Yeah.
yeah,
It can't have no point of inflection because you cannot set this one equal to 0.
right.
So that
So-
means this one is either always concave up or always concave down. Yeah, so what we do here is we look at on this side, the first derivative. If we set that equal to 0, when x is 0, y prime is 0. So we know at x, we have a vertex. Now, is it a maximum or minimum? How do we determine that? This is our critical point, our critical value. So we pick a number to the left of it, and then pick a number to the right of it, and plug it in the first derivative. And then this side. So this one's negative, this one's positive, which means this side's down, this side's up. So this is a minimum. In this case, it's also an absolute minimum.
And a local minimum as well.
And a local, yes.
So then this,
Absolutes can be, yeah, it can be local.
okay. So this one is going to be always concave.
This one's always concave up. Because the second derivative is greater than 0. It's always concave up. Which is exactly why linear equations do not have concavity. So the slope is constant. It's always 3. It's increasing. And the second derivative 0. So there is no concavity because it's a straight line. And since we're going to the second derivative, we always want the degrees to be 3 or higher to have different concavities.
3 or higher. Otherwise, it's going to be
Yeah,
one.
if it's a quadratic, then it's always going to have a constant as a second derivative. It's always going to be a parabola.
So that's kind of a roundabout way of doing it then too.
Yes, yes, very much so.
You just
Actually, it's a lot easier doing these.
just look at the local, or I mean the leading coefficient.
Mm-hmm. Now let's look at example 2. Shouldn't use that sheet. Oh well. It says determine the concavity of this function. On this interval.
We find the first derivative.
So what's 3 going to be? What's this going to contribute?
The y-intercept.
No. Well,
Oh, the amp or it's going to be the vertical
vertical shift, right?
Yeah, vertical shift, yeah.
And in this case, yeah, it's also going to be since the sine function crosses at 0 the origin, yes, then that's also going to be our y-intercept. But anything away from the x is always our vertical shift.
Okay. I almost said amplitude, and then I was like, no, that's the a. The a
of the function. Exactly.
And this
so
one is by c, right? If I'm not mistaken.
It's what?
This one is c, right? The 3 is c.
Yes.
Okay.
Yes. Let's just do pi over 2's. Forget the pi over 4's. Pi over 2, pi, 3, pi over 2, and 2 pi. So sine, let's just look at the sine function. At 0, it's 0. At pi over 2, it's 1. At pi, it's 0. At 3 over pi, 3 pi over 2 is 0. And at 2 pi, it's 0. Okay? Now, what this thing does, it raises everything up 3 spaces. So this one goes up 3 spaces. This is 1, 2, 3. This one goes up to 4. This one goes up to 3. This one goes up to 2. Oop, 2. And this one goes up to 3. So there's our graph. So now what is it asking? It's asking determine the concavity. Well, let's figure out where the maximum and minimum are. The first derivative. Derivative of 3 is 0. Derivative of sine is cosine. Set that equal to 0. So x is pi over 2 and 3 pi over 2, which is exactly what we're saying it is. Which means that somewhere between there, at negative sine, the derivative of cosine is negative sine, set that equal to 0. And that's at 0, pi, and 2 pi. But pi is between these two. So at this point here, at pi is our point of inflection. Because in order to find concavity, we have to find the point of inflection. Why do I not use 0 and 2 pi? Because they're the endpoints.
Hmm.
And endpoints cannot be points of inflection because there's no concavity afterwards. So in other words, since we have 2 vertices, the point of inflection has to happen between there.
Okay. That makes.
So let's look at to the left of it. Let's use pi over 2. And then let's use 3 pi over 2. So here, if we put negative sine pi over 2, we get negative 1. So since that's negative, this is concave down. At sine, where's our second one we're going to use? We're going to use 3 pi over 2. So we have negative. Sine at 3 pi over 2 is negative 1. It's greater than 0, so it's concave up. So far, so good?
Yes.
So now let's look at example 3. So we discussed point of inflection and everything else, so we know what those are. Example 3, here's example 3. It says determine the concavity and find the inflection points of the function x cubed plus 3x squared plus 2. So that's our function. X cubed minus 3x squared plus 2. Concavity and point of inflection. Okay, we know that it's a cubic function. The degree is 3, so the both ends and a is positive, so both ends will point opposite directions. In essence, it's an increasing function. And the y-intercept is at 2.
So
So
just
it's
like
not-
a lot of information.
What's that?
So just like that, we already have a lot of information for the graph.
Yeah, without doing any work, we just by looking at the function itself, we know what the shape's going to look like already. And we know that we have, since we factor it out, and since there is a y-intercept there, we know that this side has to cross. And this side could either bounce or it can cross. So we don't know that yet.
Okay.
It all depends on what we find from the first derivative. 3x squared minus 6x. Because if this one has 2 solutions, then we have 2 vertices, which means though we have to have 3x intercepts, which is what that says.
Okay.
So we set this one equal to 0. We can factor out a 3x, which gives us x minus 2.
We have x equals 0 and x equals 2.
So we have a vertex there and a vertex there. So since 2, the y-intercept happens on when x equals 0, that has to be our maximum. And at 2, because it's a decreasing function, it has to have a minimum there. And we could find the exact values. We plug in 2, that's 8. Minus 12 is -4, plus 2 is -2. So at 2, it's -2. So that's what our graph's going to look like. So we know we have a maximum there. We have a minimum there. Locals, not absolutes, because of these keep on going. So where is the function concave down?
At the maximum.
Nope. It's an interval. Concavity is in an interval. We have to set the second derivative. Set that equal to 0. X equals 1. So at 1, that's our point of inflection. This is the point of inflection. So from -infinity to 1, it's concave down. From 1 to positive infinity, it's concave up. Make sense? Example 4. Determine the concavity and find the point of inflection of this function. No, find the point of inflection of this function. Interesting. Good, find it. Okay. And the second page came out clear. Basically, this function is a cube root function to the 5th power, so it's going to have the same graph like that. So bring the first one down, subtract 3, or subtract 1. So the point of inflection equals what?
Well, we have to make it so that it equals 0. Well, no, you can't, because it can't equal 0.
Exactly. This one's going to be a tricky one.
Do you have to,
The reason being, because if we look at this graph, because of the 5th power, it's going to be very, very shallow. In other words, at the origin, where the point of inflection is, it's a vertical line.
so do you have to rationalize the denominator?
Even if we did that, we couldn't get it, because if we multiply top and bottom by cube root of x squared to rationalize it, we still can't use 0.
Right. Hmm.
So we know we have concave down from negative infinity to 0 and concave, but we have no point of inflection.
Hmm.
Simply because the function itself is irrational.
Yeah, this is an interesting one.
So this is what's telling us. So we can say the point of inflection is at 0. but we cannot use zero.
Right.
So we can use zero in the function, but we can't use zero in there. So the point of inflection happens at x equals 0. But the reason we can't use it is because it's a vertical, the slope is vertical at that point.
Mm-hmm. So we can't really find the exact point of inflection here.
Well, the point is something different. The point refers to this function, which we can. It'll
Mhm.
be at 0, 0. But remember, the way we find the point of inflection, we set it equal to 0. In
Right.
our example, it cannot equal 0. Since x cannot equal 0, because of the denominator being x, we know that that is our critical point. That's where everything happens. Yeah, it's just an interesting question.
So would you answer a question like this by you would answer it by saying that the point of inflection is at 0, 0?
Yes.
Okay. And is
Is that
that's because when you put 0 into x, you get 0, 0 into the point function.
so? It's at the origin. The point of inflection is at the origin, but we can't set it equal to 0 because it blows up at that point.
Right.
And actually, I'm glad you said, well, no, because originally we had this one. Because if we had x squared on the bottom, then we would have a constantly increasing function. But because here, if x is negative, the function is negative, so it goes down. If x is positive, the function is positive. The second derivative is positive, so it's concave up. But at 0, it just doesn't exist, the concavity. So it's a point of inflection. That's just an interesting question all the way around.
Mm-hmm.
Okay, let's move on. Example 5. Find the point of inflection of this one. Are they serious? Point of inflection of f of x equals x to the 4th. So the first derivative, we get 4x cubed. The second derivative, we get 12x squared. Ah. Okay, so this is another interesting one. If we set the first derivative equal to 0, set that equal to 0, what does that tell us?
That x equals 0.
So x equals 0. So what does that tell us? That's our vertex. We only have one vertex, and it happens at 0. What are our x-intercepts? We set those equal to 0. So the x-intercept happens at 0. The vertex is at 0. And do we have a point of inflection? It happens at 0. But do we really have a point of inflection?
Um,
Okay, if this is the point of inflection at 0, so let's say if we put -1 in there. And if we put +1 in there. In our second derivative. So we have 12 times -1 squared, which is 12. 12 times +1 squared, which is 12. So we really can't have a point of inflection. Because it's concave up everywhere.
Hmm.
And since our vertex occurs at 0, if we put a -1 in our first derivative, it'll be -4, which means it's a decreasing function. If we put a +1 in there, then we get a +4, which means increasing function. And at 0, so our graph simply looks like that.
Just a regular old parabola.
Exactly. And if you come think of it, look at the function. It's just f of x equals x to the fourth. There's no vertical shift, no horizontal shift. It's just x to the fourth. Example 6. This is, everybody finished that?
Mhm.
Example 6. Graph of y equals x to the 1/3 has a point of inflection at the origin because the second derivative, blah, blah, blah. Well, let's work it out ourselves. I hate when they do that. That's not an example. That's just explanation. So let's say, let's find the point of inflection. We have 1/3 times -2/3 x to the -5/3. So it's -2/9 x to the -5/3. Okay, it's a cube root. So the graph of the cube root looks like this. If we set the first derivative equal to 0, what do we get? If we set the first derivative equal 0, what do we get?
Well, it's undefined, isn't it?
It's undefined because it's a negative exponent. It's 1/3 cube root of x squared. It cannot equal 0. So there's no vertex. But because the bottom can never be 0, it's always an increasing function. Since it can never be negative.
Hmm.
So that's what the first derivative tells us. The second derivative, set it equal to 0, we can't. -2/9 9x cube root of x squared.
Still can't set it to 0.
Nope, doesn't, so it doesn't have a point of inflection, really, but because it can be negative, it can be positive because of this x right there. This one's never going to be negative. But if I put a negative x in there, what happens? If x is less than 0, what happens to the second derivative?
It's positive.
Yeah, because the top's already negative.
Mhm.
So that means the second derivative is positive, which means concave up. That's what we figured out. On the other side, when x is positive, the second derivative will be negative because the bottom's positive, the top's negative, so we have a concave down. So it goes from negative infinity to 0, concave up, 0 to infinity, concave down. And it's always an increasing function. That's an interesting question, though. Holy smokes, we have a lot of them. Okay, let's look at example 7.
Well, so for that one, do we have a point of inflection?
Yes and no. Because it happens at 0, so the POI is at x equals 0, at the origin.
Right. But it's like the other question, basically.
Exactly like the other question, right?
Because you can't the denominator can be.
Yeah, you can't set it equals 0 because the denominator, it can't be equal 0 because there's no x on the top.
Right. Okay.
Those authors sure know how to ruin a fun time.
Yeah, they do.
Example 6. This one here. The graph of, that's what we just did. Oh, we just did that one. This is example 7, I'm sorry. Example 7. A particle is moving along a horizontal coordinate line, positive in the right, with position function. So the position function with respect to time is 2t cubed minus 14t squared plus 22t minus 5 for all t greater than or equal to 0. Find the velocity and acceleration and describe the motion of the particle. So velocity is simply the first derivative. Six t squared 28t plus 22. So what can you tell me about the velocity?
Well, it's going to have 2 vertex.
Okay, so let's set this equal to 0. And we can factor out a 2. Let's see if it's factorable. Well, yeah. What times what is 33 when you add them, you get 14? 3 and 11. So they're both the same, so they're both minus 3 and 11. In this one, I could factor out a 3. So there's my factors. So my vertices occur at those 2 points. Three and 2/3. So my vertices occur here and here. So let's see what happens. I'm using this function here. 2 t minus 1, 3t minus 11. So between negative infinity and 1, I'll use 0. So the velocity is 22. And which means it's increasing. What's that? If I'm what? It should. This is interesting. This is not good. It's plugged in. Still not changing. Still not charging.
Is it your top or?
No, it's my cable frayed again. Okay, this may be it for the day. I can see it, but it's not gonna last that long because it says 5 minute, 9 minutes. Okay, let's finish this one real quick. All right, so at 0, it's increasing, so this has to be a maximum. At 2, what happens? 9 minus 6 minus 5 is -5. So it's -10. So it's decreasing. And at 4, is 6. So we have a max here. We have a min here. So it's increasing, it's decreasing, and increasing again. That's the velocity. And the acceleration is 12t minus 28. (28) 12t. (14/6) There goes. 7/3. So we have a point of inflection at 7/3. Okay, I gotta close up shop.
Okay. Death by battery.
Yeah, I have to go get another cable. All right, then I will continue here from next time and we'll do the next section as well.
Okay.
All right. Have a great weekend. Sorry about that.
Have a good weekend, everyone.
You too. Bye.